and they have a built-in checker in them, so you can actually do them by yourselves. And then I've got the second half of my tutorial is 4 solution videos where I'll go through and do the solutions to each of those 4 different tasks. So you get a chance to, I suggest you try the first task, then watch the solution video for the first task, because you'll learn more things maybe, or more ideas about how to do things after you see me do it, and then look at the second task, do the second solution video, etc. All right, but that's all accessible from the Autumn School website. So what are we going to talk about? We're talking about modelling and solving in MiniZinc. By the way, I'm at Monash University now, not Melbourne University. I moved 2 years ago. But that's okay. Everyone's using my, I realise that everyone here is using my University of Melbourne address, so they didn't realise that I'd moved. And I didn't really say anything. Anyway, so we're going to be talking about MiniZinc, which is a constraint modelling system. So you can find it all on www.minizinc.org. You can follow us on Twitter or Facebook if you so desire. And basically it's been developed over many years by Data61, which is a research institute, Monash University and the University of Melbourne. And I should say that Guido Tack is in charge of MiniZinc, and the reason that it's such a great thing that it is today is really because of a lot of work from him. And the idea of MiniZinc is it takes a high-level problem specification and it compiles it into an efficient program for different kinds of solvers. So you can place sort of MiniZinc in this idea. So we had why is it called MiniZinc? We had an earlier language called Zinc, which was higher level. It had more kinds of constructs in it, like constraint types and structures and all kinds of things. But MiniZinc was cut down a bit. But the good thing about MiniZinc is it's supported by many, many solvers. And it sort of maps to FlatZinc, so it maps down to the solver level. So there are all these languages for modeling at various different levels, and I'll show you MiniZinc, which is fairly high level, but not as high level as some other languages out there, like Essence. And essentially, MiniZinc is really a kind of tool chain, although if you use it within the IDE, which I'll show you, then you sort of won't really see this in action. But you take a model, that's the MZN file, and some data, and the model might make use of globals, and all of that is sucked in by the MiniZinc compiler, and it spits out a FlatZinc model, which is a model for that data for the solver that you want to use. And you can connect it to lots of different solvers, CP solvers, MIP solvers. Now there's also ASP solvers, SMT solvers there's SAT solvers too that you can connect it to. So that's fairly interesting, and I'll talk about that a bit more as we go on, because that gives you some power that is hard to get elsewhere. All right, but talking about a language is very uninteresting, so let's have a look at an example. So here's an example of a small constraint satisfaction problem. I've got this map of Australia and I've got 7 states, and I want to colour them all with different colours. Okay, so first I can ask you, actually, one thing I should say is that this lecture will be much more interesting for me and you if you ask me questions. So I don't know what's the best way of doing that. Possibly put the hand up in the Teams and one of the hosts can see you, or maybe just turn on your microphone and talk to me. I think that's fine. There's not too many of us, so you can just turn on your microphone, interrupt. That would be how it would happen in a normal lecture anyway. So don't be afraid to stop me, ask questions at any time. It actually makes me give better talks if I'm interrupted and I get to respond, etc. So please definitely put your hand up or just put your microphone on and ask me questions whenever you have a question. Typically, if you have a question, then many of the other people in the audience will also have it, and so we should stop and talk about it because everyone will learn.
I see that Yusuf already has a hand up. So Yusuf, do you have a question, or were you just trying to test the hands up feature?
Yeah, you're right. I just it was like I pressed the wrong button. Just to make full screen, I pressed the wrong button. I'm sorry.
That's okay. I will take away your request for control. Okay, so hopefully all of you can look at this and you can tell me how many, yeah, unfortunately we don't have a polling mechanism, but you can just talk into your microphones. How many colours do I need to colour the map of Australia? Okay, we can have someone brave. Yes, I don't know, unfortunately with Teams, I don't know how to, it'd be nice to have a little poll so we could all make our decisions. All right, someone must be brave enough to answer. All right, I can see online has its own challenges. So, do we believe we can colour it in 7 colours? Well, yes, we have it coloured in 7 colours, 7 states, 7 colours. That's easily going to be colourable. So we can definitely colour it in 7 colours. Okay, some of you might know a certain theorem, the 4-colour map theorem, which says, well, if it's a planar map, and this is a planar map because it's shown on a plane, then we can definitely colour it in 4 colours. So is that the answer? Should we colour it in 4 colours? Anyone want to dispute that? All right. So no more than 4, let's say. I need it to move. Okay. So the map is, of course, right, it's just this, really this graph here. We can put the nodes and the edges and join them between them. So let's think about how we would put this into MiniZinc, into a formal modelling system. So the bits that we're going to need are, we're going to have decision variables and their possible values. And so for this example, the decision variables are for each state, what colour does it get, right? We're going to have constraints. So we're going to have for each adjacent state, they must have different colours, or they can't have the same colour. And typically in optimization, typically we do optimization, not just satisfaction. We say, okay, we're trying to minimize the number of colours. Okay, so in fact, there's 2 kinds of variables actually that we will see in models. The parameters are the knowns or the inputs. So typically we'll build a model to answer more than one question, and we want to read in some data which defines the particular question that we're answering. So that's going to be one thing we're going to need. And then the decision, so there's the 2 variables. So parameters are just known input things, and decision variables are the unknowns. They're the interesting ones. That's what the constraint solver is magically going to decide for us. Okay, so if we start building up our MiniZinc model, then let's say the number of colours we'll start with is 6. Yep. So we'll say there's a maximum number of colours is 6. So there we just declared this NC variable. It's a parameter. We're giving it the value 6. Right, we could have just used 6 wherever NC was in the model, but of course we might want to come back and say, well, actually we only need 4 colours, so we could change NC to 4, and then we'd be doing, you know, we'd only change one part of the model and everything else would be the same. Okay. So how do you think about parameters? They're like variables in C, Java, or Python. So they're declared with a type, something like int, bool, float, setup, int. They have to be assigned a value and only one value. So they're not like variables in C in the sense that x equals 1 and then I can later say x equals 2. They can only ever have one value. That's true. Basically, we're in a declarative language here. So variables really are placeholders for one value. But parameters will have to be, you'll have to be given their value from somewhere. It can be from separate data file or it can be given in the model. But the parameters have to come from somewhere. Right, so we can write int I equals 3. So this declares the parameter I and sets it to 3. we can just say int I, which means I is a parameter. And then this I equals 3, this is an assignment. And this assignment essentially could be given in a data file. So a DZN file is where the data goes. So if for this particular data we want to set the parameter I to 3, then we put that in the DZN file. And we're going to see parametric models. Okay, so the names of parameters have to be things that start with a letter, followed by letters, digits, and underscores. So that's a typical kind of identifier description in many languages. Okay, parameters, easy enough. What about variables? Okay, so we have to declare a variable for each of our states. So you can see we've got a WA variable for the colour of WA, NT for NT, SA for South Australia, Q for Queensland, NSW for New South Wales, V for Victoria, and T for Tasmania. And now you can see that there's this var declaration up here, which tells us these are decision variables that the solver is going to be responsible for giving a value. And we're giving them a subset, so they have to take a value from this range, 1 to 6 in this case. Right, so we're going to map each of these states to a colour from 1 to 6. We'll come back and show you different ways where we could have different kinds of colours later on, different ways of representing colours, which might be more intuitive. Okay, so what are decision variables? So these are exactly like variables in maths or in any other kind of declarative language, right? But more like think of them as math values because you're not going to give them a value. This is the solver's role. The aim of the solver that we're going to run the model with is to decide for each of these variables what value it should take. So they're declared with this var keyword and the type, what kind of variable type they are. You can declare them as we saw with a range or a set, the variable domain. So for here example, we've got this variable I can take a value from 0 to 4. We could have written it this way, right? 0, 1, 2, 3, 4. That's just another way of writing this set from 0 to 4. We could have written it this way instead. We could have said, well, this is just an integer with no bounds on it, but we'll add some constraints which will effectively require it to only take the values in between 0 and 4, right? So all of these examples are equivalent. Hopefully you can now see the MiniZinc IDE. And so here's our model that we just saw before. I can choose which solver I'm using up here. G-code is a sort of default, so let's start with that. We can run it like I did before, and you can see what happens. Down the bottom here. Right, so here's the solution. So we've just, the model as is, it prints out all the variables, their values at the end. And this says, okay, we found a solution. So the single bar means we've found a solution. The double bar means we've found the optimal solution. So there's no better solution. Later on, when you're running big models, you may not want to hang around to find the optimal solution, or it might be just too hard. And so you'll just run and get whatever solution happens within the time you're willing to spend. And so you should be able to notice then that the number of colors that we used was 3. Okay, so we didn't actually need 4 colors to color Australia. We could do it with just 3. We knew we could do it with 4 because of the 4-color map theorem, but we didn't need any. Okay, so there is our first look at MiniZinc in action. Fine, we're back to where we were. Okay, any questions about that? Is there a chat you can type into? Because one of the simple ways of asking a question is, if you're really shy, is type the question into chat and then Bart or someone will read it out to me. So you don't even have to speak up. But as I said, the more questions you ask me, the better this talk will be. Okay, too obvious, too easy. Don't worry, we'll make it hard. Okay, so the first programming task is a cryptarithm puzzle. Here's an example of one, right? So this is easy. This is meant to be arithmetically true. So we've got to pick digit values to go for THIS and EASY, so that this holds. And the other part of a cryptarithm is all of the letters have to have different values, right? And the other thing is, because these are meant to be proper numbers, T, like the leading letters, can't be 0, right? So I'll just show you the answer of this one. In fact, in the first task, we'll give you another cryptarithm. The first thing you have to do is, we'll give you the answer, you just need to run it. So it's really there to check that you can get MiniZinc to work. But here it is in all its glory. We've got the variable declarations, right? So T has to be a digit because it starts one of these numbers. It can't be 0, right? Because we don't write, for the number 15, we don't write 0, 1, 5. Typically, we just write 1, 5. H is from 0 to 9. I is from 1 to 9 because it starts again, this word. S is from 0 to 9. E, again, starts a word, is from 1 to 9. And now we're starting to use some inclusion. So we're going to include this all different .nzn. What that's doing is including a global constraint, which we're using just below. So the global all different constraint says, well, here is an array of decision variables. They all have to take different values, right? So it's a bit like what we saw not equals in the Australian map problem, which was just saying the two things have to take different values. So here we're making all of them take different values. And then finally, the other constraint is the cryptarithm, which says that mathematically, right? So 1,000 times T plus 100 times H plus 10 times I plus S, that's the value of this mathematically, when I think of all the digits, plus 10 times I times S, that's the value of this mathematically, is equal to easy mathematically. Right, and here we've added a solve satisfy. We could leave it out because if there's no solve item, then by default it is. Run it, and there we go. So if you try to write it out, 1974 plus 74 is equal to 2048, right? Arithmetic holds. Okay. Slides. Right. Okay, and as I said before, the first task you'll be given, which you should attempt after this, is to do some cryptarithms, a few of them. And hopefully that should give you an idea about things in MiniZinc. It's fairly straightforward because you've seen one. Okay, so we've actually already used them, but one of the critical features of MiniZinc is arrays, right? So when we're writing generic models, we're basically going to be answering questions about a variable-sized number of decisions, and the way we do have a variable number of decisions is to build an array of them. So you declare these as array with an index set of some type, right? And it contain everything except other arrays. But you can have 2 and 3 and 4 dimensional arrays. We'll see some 2-dimensional arrays in this slide. We don't typically use much beyond that. And the index set has to be a range of integers. So interestingly, in MiniZinc, you can have an array which is indexed from 5 to 10, for example. It doesn't have to be from 1 to something or 0 to something, which is sort of allowing both possibilities to be used, whichever one you prefer. Although it is true that MiniZinc really naturally thinks of array as indexed from 1 to 10. So the arrays we build up, so if I write this array literal here, v1, v2, v3, that's an array of length 3. The default index set of this is 1 to 3. Right, if I build this array, I concatenate the numbers 1, 2, 3 to the numbers 4, 5, 6. The indexes for this array that I built from concatenation are 1 to 6. You can have 2D arrays and there's some special notation. So you can open a 2D array with the square brackets and the vertical bar. Then you have the row is separated by commas. Then the vertical bar separates the next row from the next thing. So the elements in the row, then a new row, elements in a row. And arrays, 2D arrays have to be square. And I'll show you some examples of coercion of arrays, which we probably won't see much of. Okay, and the important thing about arrays is that we can now do some interesting things. Okay, so we can have a lot of built-in functions which work on arrays. So sum, product, min, max for all exists, and we'll see lots of examples of these. And basically you can construct arrays using comprehensions. So those of you who've seen other declarative languages, you might be used to comprehensions, and I guess comprehensions are now in some procedural languages as well because they're so useful. So this builds an array with 10 elements in it because I is varying from 1 to 10, which has this expression in it, x minus I, right? So x minus 1, then x minus 2, then x minus 3, up to x minus 10. And so x could be a decision variable, right? It doesn't have to be a fixed variable. We could be building up a set of decisions, essentially. And so the format is basically, here's the expression you're going to build multiple copies of. We can have numbers of generators, and we can have a where condition, which prevents us from generating all the possibilities. So I can write this, or I can also, it says I and j are taking values from 1 to 10. Okay, I varies slower than j. So first we give I a value, and then we give j a value. But we're going to require that I is not equal to j. So rather than looking at the 100 possible things and generating 100 possible constraints, of course, it would be a bad idea to generate this constraint for I equal to j, because that would then say x of I is not equal to x of I, which is a constraint which is never true. So this statement would never be able to hold. So we're looking at all the i's and j's. So this is really an all different constraint, actually, right? So it says, look at all the i's and j's, except for them where they're the same, and generate this not equals constraint between them. So this is the generator syntax where you essentially put the generator information in the parentheses and then the expression you're trying to build. This is actually syntactic sugar for this. So here's the generator, right? We build up an array with all these expressions, and then we apply the for all function to it, which means we're saying all of these expressions have to be evaluated to true, right? So it's just the conjunction of all these things. But we'll typically use generator syntax for these common kinds of things like sum, product, min, max for all. But if you think about them, really, these are just functions which take an array as an argument. And when we write this down, we're actually building this array and then applying the for all to it. Okay, remember to stop me if you have questions, because this can be a little bit confusing. All right, so let's have a look at an example. So the N Queens example. So for logic programming, this was a classic example we used, and for early constraint programming. So this is a a problem dear to my heart, because basically every logic programming or constraint programming talk should really have n queens in it somewhere. So the problem is to place n queens on an n by n chessboard so that no queens attack each other. And just for those who haven't played chess for a long time, a queen can attack horizontally, vertically, and diagonally. So for example, this queen here can attack the horizontal, the vertical, and both diagonals along here and along here. And you can see that there's no queens in any of those spaces. So none of these queens can see another one. So this is a solution for 8 queens on an 8 by 8 chessboard. All right, so here we can start to use our arrays, because notice what we're building this model for n queens, right? It'll work for any size, any square size chessboard. So we've got this integer n, that's a parameter telling us how big the chessboard is in width and rows and columns. And we're going to, the decisions we have to make. So we know that there can only be 1 queen in each row, because if we had 2 queens in the row, they could take each other. So the way we're going to represent our decisions are, for each row, we're going to put a queen in there. We also know that there has to be 1 queen in each row, because if there's 8 queens and we can't have 2 in the same row, then we know that we have to put 1 queen in every row. So for each of the n rows, we're going to choose the column in which we place the queen. Okay? So here's our array of decision variables. And then we have to constrain them so they can't take each other. So the first one is the most simple one. In fact, we've seen it before, right? So we look for all ij pairs which are different, right? Because obviously we don't want, we're going to have the 2 queens in the same queen, the same column must be the same. We're going to say that the column for this queen is different from the column of that queen, right? Because we know if we put 2 queens in the same column, they can definitely take each other vertically. So the diagonal is a bit sneakier. We're doing the same thing. We're iterating over all pairs of ij. And we're saying, if we take the queen in row I, so this is the column for the queen in row I, and we add I to it, and the queen in row j and add j to it, they have to be different. So the way to think about this is, if we have a queen, I hope you can see my hands reasonably. If we have a queen in row 1 and a queen in row 2, so imagine the queen in row 1 is in column 1, and the queen in row 2, yes, this is the wrong way, yeah. Let's say the queen in row 2 is in column 4. Right, let's do it that way. The queen in row 1 is in column 4, the queen in row 2 is in column 3. Then they're diagonally next to each other, right? But if we take q of I, which is 4, and add I, which is 1, we get 5. We take q of j, which is 3, and add j, which is 2, we get 5. So basically, these diagonals, this constraint stops 2 queens being on the same diagonal like that, right? Because basically, if you can think about it, q of I plus I is kind of like the Manhattan distance from the corner point, right? And so that means that all the diagonals like this are equal Manhattan distance from the corner point. We can't have them this way. And this q of I minus I is not equal to q of j minus j, is exactly the other one. It's the columns like this, right? So basically the diagonals like this, and we can't have 2 queens in the same diagonal. So here's our model. We're satisfying it, and we're going to output the queens. If we didn't have this, we'd get a similar result. We'd just get the default printout saying q is equal to something. All right, we can better this model, right? So let's introduce sets, at least to make this model a bit more understandable. We're not going to use sets here for anything very clever, but it will make our model more understandable, I hope. So sets contain integers or floats or bools, but the only variable set, so you write them as set of int and then x. So this is a fixed set of integers, a parameter. So there's no var there. So you can write set expressions like this. That's the set containing 3, 5, and 7. You can write ranges as a floating point range. And you've got set operations on them, union, intersection, div, etc., subset, superset. The main one we'll use is in, right? So this is an element of the set. Cardinality is also used. Okay, so the nice thing is we can use a fixed set as a type, essentially. So let's have a look at that. So here was our model. Now notice there's really two uses of 1 to n in this model. So here, 1 to n, this is saying in this row, right? So for each row, we have to pick a column for where this queen goes. So we can make this model much more understandable by really just naming those two things separately. So we know the set of rows is 1 to n. The set of columns is also 1 to n. So really these sets are the same. But now we say, okay, this is an array for each row of which column the queen is in. It's much clearer. And we should be careful, right? So these are indexes into this array. So of course they are talking about rows. We're looking at the ith row and the jth row where they're not the same and saying they're not equal, right? So just allowing us to give a name to this set and then use it in our definitions and use it in our indexes, our generators here, makes our model much more easy to understand. All right, so because they're the same, whoops, because I in rows, j in rows is the same, we can just write it this way, I comma j in rows. And lastly, we should actually think about this a bit more. We don't actually need it for I not equal to j. So imagine I was row 5 and j was row 7. Then we're going to say that the q in row 5 is not equal to the q in row 7. But what if we flip them? What if I is 7 and j is 5? Then we're going to write the constraint q of 7 not equal to q of 5, which is the same. We've already written it. We wrote it for the pair I equals 5, j equals 7. We don't need to write it again for the pair I equals 7, j equals 5, which means we only have to iterate over the pairs I and j in rows where I is less than j. Right, so basically you only have to look at half the array to set up all the constraints, because that's all we need. Otherwise, we're just duplicating constraints. So this is a very common pattern when we're doing something over all pairs of something. We iterate over all the pairs, and then we only look at the pairs where I is less than j. And that'll be all the different pairs in some array. All right, now you can, I'll show you, hopefully it'll work. We can look at this problem for 10 queens and we can actually see how many solutions there are. Okay, there's quite a few. Well, actually, I think it says there. Number of solutions is the 724, I think. But there's a very big search tree. So one of the things we can do with MiniZinc is look at these search trees. So that's surprising, right, for such a small problem. So once you start going for even bigger sizes n, you're going to get even bigger solution sets. So we want to think about, so whenever we're building a model, right, we want to think, how can we make it better? How can we improve that model? Okay, maybe I'll try and show you GIST as well, because it's useful for the debugging as well that you'll want to do. So I should demonstrate it. So let's bring up. Okay, so here's n queens. So if we go to the G-code GIST solver, we can run this and we want to enter our parameter. So let's just do 5 for simplicity to make it smaller. Now, can you see a little pop-up window? This is one of the dangers of this thing. On top of my n queens, can you see a little window or not?
No.
Sounds like no. No, so okay. I could probably, yeah, this is a danger of pop-up windows and sharing screens. So sometimes it does work. Now I could probably, let me just first prepare the window to show you all solutions. Okay, I'll probably switch to sharing the little window now that it exists. If I can see it. Okay, I can. All right, so unfortunately I can't see you the model at one time. So this is what GIST will output for the queens, right? And you can see there's many solutions here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So each of these represents a decision. The surprising thing, if you think about it, is you've got 5 queens, which each have 5 possibilities. So the total number of possibilities you can look at is 5 to the 5, right? That's a big number. But the
Peter, I cannot hear you. I can see your screen and the window with the tree, but I cannot hear you.
every time, yeah, now you should be able to hear me again.
Yes, yes.
Sorry. I can keep it on this, maybe that's safest. So then the microphone won't go away. You get a worse picture of me, but that doesn't matter. And so we've got the little G-code window, right. So there's the G-code window, hope we can see it. But if you think about it, it's rather surprising, right? That we can, so the raw search space here is 5 to the 5. It's got 5 variables that can take 5 values. But really the search tree has only got something like 13 decisions in it, right? And we can, yes, I've lost my little window. A bit hard for me to run this without the help. Okay, but anyway, I advise you to play around with just a bit, because that'll help you understand what's going on in your models. Okay, no, I didn't want to go there, I want to go back to the slides. Goodness me. All right, let me move this. Okay. All right, I'm going to, I'll soldier on. My apologies for this. So yeah, it happens very rarely, but it's happening more now, just that I can't use my mouse. Of course, that keyboard's not connected. All right, let me get that keyboard out of the way. Okay, so we want to be able to improve our model. So, so this is one of the reasons that we want to think about using a solver-independent modeling language like MiniZinc. So when we got our problem, then we build a model of it, and then we'll have some data. Those together will combine to give us what we call a problem instance. So a particular, like n equals 5 for n queens. So we can use MiniZinc to generate a program which we can give to a solver to generate solutions. We can also use it to generate a different program for a different solver. So this means it's very easy to compare different solvers. And this is important because typically for the problems that we're dealing with here, they're NP hard. And so there's likely to be no magic bullet. And one solver might be a lot more effective than the other solver. And for a different model, it might be the other way around. So one of the powers of a solver-independent modeling language like MiniZinc is that we can just change whatever solver we want to deal with and try again. And for example, for the 4th task in this, I'm suggesting that you don't use Bellodi, but one of the other solvers. So there are many different kinds of solvers, and in fact, for each different kind of solver, there are many implementations. So mixed integer programming solvers, there's commercial solvers like Cplex and Bellodi, and there's Skip, and there's also OR CoinBC, which comes with a MiniZinc IDE. So that's a mixed integer programming solver. So these are very good for problems which are mainly linear constraints. There's many constraint programming solvers, so GCO is one of the ones that are built in and chucked as well. If you're interested, you can play with MiniCP or Minion, other solvers. And of course, you might be aware that there's lots of SAT solvers out there and lots of SMT solvers. There are not so many SMT solvers out there, but there are plenty of number of them. And this is what I was talking about. There's no best solver, really. It depends on the problem you want to solve. And so once you've got many ways to model, then you can have an order of magnitude difference in the execution times for the same model on different solvers. So one of the things that I discovered a couple of years ago is that I had a visitor and he does rotating workforce scheduling, and we build a rotating workforce scheduling model in two ways. We built it in a way which I thought was perfect for a CP solver, and we built it in another way which we thought was perfect for a MIP solver. And it turned out that our model, which was perfect for a CP solver, was actually more efficient for the MIP solver, and the other way around. The model which I thought was perfect for the CP solver was more efficient for the MIP solver. So even experts like me don't necessarily know which solver is going to be best for which model. So that's why being able to try this, is being able to try different solvers is important, because really in the real world, modeling is this iterative process, right? You'll basically build a model, it'll be wrong, or it'll be too simple, or it will make some assumptions. We'll look at the solutions and we'll come back and want to remodel. We might add constraints, we might relax constraints, etc. We might, many things, particularly if you've got a client there, the first solutions you'll show them, they'll go, well, this is meaningless. It doesn't attach to the real problem that I've told you about. So this process is expensive and iterative, so we want to be able to do it as quickly as we can. So modeling is like programming, right? So you can write inefficient and efficient models. So remember, the model is declarative. It's really just specifying how the problem should be determined with constraints. And the solving approach is not, right? The solving will be very different for different solvers. And this, even though I've just been going on about how solver-independent modeling is super important, because we can take the same model and run it on different solvers and see which one's better, the more you understand about the solver, the more likely you can write efficient models that will be useful for that solver. Okay, so let's talk about some simple things that are worth getting right. So if you write var int in a model, you're basically telling the solver, this is just any integer, right? And so it could take any value. And so that gives us a lot of choice. But if you know that it can only take a restricted range of possibilities, then you should have those in the declaration. So if you know that it can only take values from the lower bound L to the upper bound U, then declare it as var L.u and then the variable name, meaning we can only take those values. And that's just going to remove some choices from any sort of solver. So that's usually very good. You should avoid introducing unnecessary variables. So we don't want to add more variables than needed. Variables, let's say, which don't take part in any constraints and don't really matter. So one of the classic examples of this is we have, let's say, we're representing a graph by a connectedness matrix, right? And so there's a 0, 1 variable saying whether two nodes are equal in this square array. So we only actually need half of that array, right? Because we only have to care for each pair of variables if I is less than j as they connected or not. So we've got two things. We can either set all the other half to 0 and make sure that they're not variables so that the solver is not trying to solve them, or we can make this array symmetric, which is normally how we represent an adjacency matrix, and copy the other one. So there's only one copy, there's two copies of the same variable. Simply making loops as tight as possible. And sometimes it's necessary to check the generated flat sync. I'll try to remember to do this in one of the examples I show you. And that can just show you how many additional variables are introduced and if constraints are being decomposed in a way that you don't understand. But we probably don't have enough time to do too much of looking at flat sync. Hopefully, the idea is you should never have to look at flat sync. All right, so simple things there. Try to make your decisions as tight as possible. Try to make your loops as tight as possible. So like that example in the Queens, right? We had this loop which was for I not equal to j, but I could just make the model better and smaller by putting I less than j. Okay. But the most important thing, and sort of one of the great powers of constraint programming modeling, of which MiniZinc is a constraint programming modeling language, is that we have this notion of global constraints. Okay, so global constraints capture common model structure, right? So structure that happens in many different kinds of problems. And there's a global constraint library. You can see it in the MiniZinc documentation in the libglobals.html. There's lots of them. And you can import them all by this include globals.mzn. You've already seen this. We've imported one. So we imported all different in the this is easy case, right? So that you can import them one at a time, and then you import just the ones you use. That's just to make sure that you don't start using ones you didn't expect, but you can always be lazy and put include globals.mzn, and then they're all available. And the advantage of these global constraints is that you typically get a much cleaner model, right? They're typically smaller. And for some solvers, particularly for CP solvers, these global constraints will actually be converted to dedicated solving algorithms. So you get much faster execution. And even if you don't, even if you use a solver like a MIP solver, which doesn't have global constraints in the solver, you can still get better translation to flats for MIP, right? Because the model or MiniZinc understands what you're trying to say with all different, and it will translate it in a way that's best for the MIP solver or best for the SAT solver. So global constraints are one of the great powers of constraint programming. All right, and so you should think that what we were doing, remember, when we were writing down the Queen's example, was we're saying that no two Queens could be in the same column, and no two Queens could be in the same diagonal like this, and no two Queens could be in the same diagonal like that. All right, so if we think about it, well, this is an all different constraint, right? So we're saying for each of the columns you pick for the Queens in each row, they all have to be different. So no two Queens can be in the same column, right? And here we've got the include all different .mzn. Otherwise, if we don't do that, we're going to get an error message saying, I don't know what all different means. Okay. What's a bit more subtle is you can also use all different for those diagonal constraints. Because if you thought about it, we just built these expressions, qi plus I, and we said that was different from qj plus j, which means that all of the expressions qi plus I for all of the different, well, that should be rows, I in rows. This is one advantage of not being in full screen. I can fix it on the fly, right? All of those qi plus I expressions also have to be different because qi plus I sort of maps to one of the diagonals like of this form. And so we're saying that each of the diagonals used by the ith queen have to be different. So that's an all different constraint. And here, so it looks a bit magic. Remember, this is just generator syntax. This is the same as saying build up an array with qi plus I for all I in rows. So build up that array and then apply the all different to it, right? Which is how we used all different here. Here was an array of variables. We want them to be all different. Here's an array of, this is essentially building up an array of expressions, qi plus I, and requiring that they're all different. Right? So the interesting thing is the generator syntax is for all and some isn't special. We can use it for any function on an array, a single array. And the other diagonals are obviously the same, right? We were saying that all of the expressions, so qi minus I had to be different from qj minus j, which means that all of those expressions have to be different. So this all different constraint captures that completely. Okay. So if we take our original model without all different, right, and we wrote down all of the solutions and we looked at how long it took to do that, we generate 10,545 nodes to generate the solutions here. You can see them sort of split up into decision nodes, failed nodes, and success nodes. So this is for n equals 13, so a 13 by 13 queens, and it takes 7.5 seconds. So when we add the all different global constraint, right? So if we're using G-code, which is a solver that understands all different natively, it's interesting, we don't actually get that many fewer nodes, right? We get 13% less nodes. We take actually, we get a more than 13% reduction in time, right? But you can see the search tree has changed shape. It hasn't changed shape that much because, in fact, for this particular example, n queens, a lot of the power of all different isn't required. So it's just working more or less like essentially we wrote all different as a whole lot of not equals, right? There are two different ways of writing the same constraint. But we did see this reduction. But this is not the best case for all different. Many cases for all different, you get massive reductions in the size of the search required. But this is still substantial, and of course, as n grows, this reduction improves. Any questions? I've been going for quite a while. Nope. As I said, the more you interrupt me, the better this tutorial will be, I can assure you.
Sorry, may I ask a very simple question?
Absolutely, the simple question.
Yeah, I'm wondering, like, using the all different does syntactically makes the program much neater, but can you explain briefly how it actually accelerates the execution of the program? Thanks.
Yeah, I can do that. That's a really good question. Okay. Oof. So actually, it's the all different constraint is very cleverly built. It actually relies on maximal matching. And so let's say we have one variable here, another variable here, another variable here. We're basically going to draw edges between, we draw edges between the variables and the values. So this is a value, let's say 1, 2, 3. Okay, let me do that. So let's say x can take the values 1 and 2, right? Y can take the values 1 and 2. And Z can take the values 1 and 3. So we draw this little graph like this. Now, each of those variables can take a different value. So there's nothing wrong with this picture, right? But actually, all different so if you treat all of the inequalities together, X can be different from Y, sure, because they can take different values. Z can be different from X, sure, they can take different values. Y can be different from Z, yes, they can take different values. But if we think about them all together, we'll find that, look, X and Y have to take the values 1 and 2 together, right? If X takes the value 1, then Y has to take the value 2. If X takes the value 2, then Y has to take the value 1, which means that Z can never take the value 3. Okay, so even though the not equals constraints can't see anything they can do, essentially not equals can do nothing until one of the variables become fixed. The all different constraint can already fix Z to 3 because it knows if it tried to put Z to 1, there would be no solution for one of X and Y. Okay, so that's sort of showing you, once I put all the constraints together, then I can do more complicated reasoning. And actually the algorithms behind it are based on maximal matching, and they're very sneaky and interesting. Okay. So one thing that we may come back at the end, and I'll which I'll play around with to show you, is that as a naive modeler, it's sometimes difficult to know which global constraints are out there. But there is a tool in MiniZinc, and you can see it, you can drop down. It's a pseudo solver. It's not really a solver, but it acts like a solver in MiniZinc. That if you give it a model and some input files, it'll find submodels, right? So it'll look at little parts of that model and see if that submodel was equal to a global. So essentially what it'll do is it will find globals that are actually in your model, but you haven't called by their global name, right? And so you can then look at the globals that Globalizer suggests, and you might be able to improve your model by replacing part of your model by this global, or even just adding the global. Because one thing that's true in constraint programming is often it's worth having two copies of the same constraint, as long as they don't act exactly the same way. As long as one can give more information in some circumstances than the other, then having two copies isn't so bad, right? Because they might work together to together generate information. All right.
I have a question here about the globalizers.
Yeah.
Do they only work instance-based, or do you also have a method that does it at a first-order level, say by reasoning, seeing that?
Yeah. No, we would love that. So it's not instant-based, as it sort of says here. So you can give it multiple instances at once, and it'll find only the candidates which are true for all those instances. Okay, and typically why this is important is what we want to find is, of course, a global which is true for the entire thing. But to really prove that it is true, we basically need some kind of theorem proving to prove that for all possible ways of parameter that these constraints imply this global constraint, right? And so since that theorem proving isn't, theorem proving is difficult to use and not that strong, we haven't done that, so we're just using it as a suggestion tool, right? But the good thing is, basically, if you give it 4 different models, unless you're really unlucky, most of the globals it'll suggest are exactly correct, because you'd have to have something special in your data for all 4 of them to generate some global which looked good and worked on across all 4 models. So so we sort of find that it is almost always correct, right? But we can't prove it, or to prove it, we would have to attach a theorem prover, etc., etc. So to fully automate it is tricky, and that's sort of one of the things you'll see. I'll talk a little bit later about symmetry stuff, and we have automatic symmetry detection stuff as well. And again, you don't want to do it per instance, right? Because per instance, the globalizer takes longer to run than the model. So why would you run the globalizer on let's say you've got a big example of your problem. You don't want to run globalizer for this big example if it's going to take longer to find the globals on the big instance and then convert that. And then you can add them to your model. It'll be correct because it'll check, and then you run. But you already spent more time than you would have if you just ran the original of them. So we definitely like this idea of model-based, improving the model. So that's what Globalizer will do. It'll allow you to improve the model. And it's surprising, really, how small the examples can be for Globalizer to kick in and find all the useful constraints. I mean, sometimes there's some other cases where if you only look at size 2, things are special. But as long as you're up to 2, even size 3, as we know, the difference between 2SAT and 3SAT is a very big step. You don't have to go very big before Globalizer is returning things which are almost always exactly what you want. All right. So one of the key things and one of the ways, the key tricks behind MiniZinc is actually this notion of predicates. Right. And I think this is probably the biggest step that we did in MiniZinc, because what is true of when we're building MiniZinc, even for all the CP solvers at the time, this solver had this global, this solver had this global, this solver had these other globals. No solver had all the globals. And so if you wrote a model and you wrote it for this solver, and then you wanted to run it on this solver which didn't have this global, well, you had to change the model. So predicates allow us to take a definition or build our own predicates or constraints, a system of constraints, and then we can use that to control how a global gets rewritten. So in the globals.mzn library, all of the predicates are actually defined in terms of smaller common constraints. Okay, so the all different in the globals.mzn is defined actually as this, right? We take an array of integer variables of some length. That's what this array int means. We don't know what length it is. We don't know what its index set is. We iterate over all pairs in the index set. So all pairs for the index of the array you're given, where I is less than j, like we saw before. So that's all the different pairs. And we assert x of I is not equal to x of j. So really, essentially, what we saw happened in the n-queens problem, where is I had written this originally in the model, and then I said, oh, replace it with all different. Okay, so if I replace it with all different and I use just the standard library, then actually the standard library will replace the all different by exactly what I had. So I'll be back to where I started from. But of course, the advantage of this is that if I used it for G-code, for example, which has a built-in all different, it replaces the standard definition by its own definition, which means it gets sent the all different as is, unchanged, and it can use its powerful all different propagator to find out what's going on. But what happens, what it does mean is if I take a MiniZinc model, it'll guarantee to run on every solver, because the globals you use, whatever globals they are, will either be sent to the solver in a form that it understands, or they'll be converted into constraints which it understands, right? So that's the kind of power of MiniZinc, is that this notion of predicate. And so we can write, if we just write predicate all different and then put a semicolon here, so we give no definition, then we're basically saying that for this solver, it understands all different. And so we just send it to the solver as is, right? And so for different solvers, there's different libraries, and that changes how the globals are interpreted, right? So during the compilation, the global is decomposed. If this is the existing definition for all different, if there's a different one, so just say all different with no definition, then it's sent direct. And for a MIP solver, we would not use this definition of all different, right? This is not the right way to write MIP, to write all different for a MIP solver. We have a different definition of all different, so it's decomposed into a different set of constraints. And that's sort of the big power of the sort of global constraint view of the world, is that essentially we have this all different, which is a really common pattern in discrete optimization problems, because all different is exactly this assignment problem, right? All different says, here's a set of decisions I have to make, right? And let's say they're tasks, which I have to assign to people, right? So for each task, the decision is which person gets that task. But I know that every person can only get one task. So that's an assignment subproblem. So that's what predicates actually capture. They capture common patterns in discrete optimization models. Okay, so we'll come back and show some examples of that in a moment. Now, we're out to.
Maybe another question here.
Yeah.
Yep. Is it possible to replace, so now you have it specifically for integer variables. Can you also template them with?
Yeah, so you can have all different for float variables. So if I change this to var float, so I can have both these, so different types are essentially different predicates, and we can look up on the type to find which one we're talking about.
And could you, with a single statement, declare all of them? Like for every type, I have an.
I can. There is some parametric polymorphism, which is probably okay here. I mean, I can do $t, right? Because not equals is valid for all the base types. So $t is only for var, float, int, and set, right? So all of this expression is interpretable for all those base types. But it isn't a very complicated type system, right? So we very rarely use parametric types because typically models, so there's a bit of use for it in the globals library, but it's not it's not like a programming language where a lot of the kind of built-in structures we want to be parametrically polymorphic or have other kinds of polymorphism. So we have the simple like overloading, just type overloading polymorphism, where we can essentially have different things, and we do have parametric polymorphism. We'll show you, when I show you enumerated types, this is the most used polymorphism is essentially that we want to introduce enumerated types, which are really sort of names of objects, which for a solver will eventually be integers, but we want all of our predicates to work on them directly. So there's a couple of ways that that works out. So that's it's really there to make enumerated, well, so the type system is interested in enumerated types because they're very common in models. Okay, so we can build really complex constraints, and this is one of the great powers of a modeling language like MiniZinc is we can build up really, really complex constraints using the Boolean connectives. It's also one of the dangers because for naive modelers, they see all the power and they tend to write things how they're used to. Particularly, we have if then else in the language, and a lot of beginning modelers try to write if then else statements because it's like the procedural programming that they're used to. And so you can write this kind of pseudo procedural models, which may not necessarily be the best way of doing it. So, but one of the powerful things of is these Boolean operators is that we can write down expressions like this, right? So we can essentially give a Boolean name to the value of a Boolean expression. So this is called reification. So this B variable is true either if y takes the value 0 or x div y is less than equal to 100. Right, and so you can see that this other interesting thing, which I probably won't get into, but I'm happy to talk about if people do, is that there's this other interesting problem. So what is this meant to mean? Oh, actually, this might be a good place for a poll just to stop and actually force you to think. If you can prepare a poll. So what should be the value of B, okay, if y takes the value 0 and x takes the value 3? Should it be true? Should it be false? Should it be division by 0 error? Should it be unconstrained, take any value it wants?
All right, we've got the poll.
Okay, thank you, Bart, for being a quick typist. So be quick about it. I just realised that we're more than halfway through and I have plenty more material to go. All right, let's have the results.
100% says true. That's 9 people.
Yeah. So that's exactly what the y equals 0 here, right? Since y equals 0, this is true. This actually in MiniZinc, if y equals 0 and x equals 4, this just becomes false because the division by 0 becomes essentially a bottom, and then we say bottom less than equal to 10, and then we have a bottom in a Boolean context, it becomes false. So this becomes true or false, in other words, true. All right, I got to get the move on, I've realised, because of course I have too much stuff to talk about. So one of the examples you look at is a scheduling example, and the kinds of things that you can build with a predicate. The predicate is this no overlap constraint. So we take an array of the start variables, right, the start times for tasks, an array of their durations, and then we can make sure that none of the tasks overlap in duration. So we look across all pairs of tasks. So this time it's both ways. Yeah, no, we don't need both ways. That should be I less than j as well, because it's symmetric on I and j. So this is the end time for task I, the start plus the duration, that should be less than or equal to the start time of j. Or this is the end time of task j, that has to be less than or equal to the start of time I. And you can see that those two constraints together will force either I to be before j or j to be after I. And so we'll get no overlap. So you can make use of this no overlap in task number 3, which you can get to afterwards. And I need to be in the right version of this. Okay. So another really critical power of constraint modeling languages is we can write this x of I, right, looking up an array with an index I, but something that you may not be used to is that I can be itself a decision variable. All right, so this creates an implicit constraint on the array, which is called an element constraint for historical purposes. But to show you just a trivial example, if I give you n items and here's their cost, okay, and I can pick, I'm going to pick which item to take. And here I'm going to minimize the cost of the item. So notice this is a decision, right? So I'm going to minimize the cost of the item, means I'm going to look across these costs, find the minimum value, and that item value will be that minimum possible value. Okay. So let's use that. Let's use that for an example. So this is the old-fashioned stable marriage problem. Okay. So we're given n men and n women, and we're basically going to pair them off as husband or wife. And we want to find husband or wife patterns, right? So a pairing such that all the marriages are stable. So what is a stable marriage? So it means if you've got a man, then if they prefer another woman, O, to their wife, then O prefers her husband to M, right? So this man would like to swap to the other woman, O, but O prefers her husband to M, so she's not going to swap. If W, similarly for the women, if W prefers another man, O, to her husband, then it must be that O prefers his wife to W. So even though this W wants to swap to pair up with O, he prefers his wife to W, so won't do the swap. So this is a stable marriage. So an example of a stable marriage, some example from some well-known TV show. Okay, so let's imagine that Howard prefers Penny, but is married to Bernadette, and Penny prefers Leonard to Howard. Right, so even though Howard would like to pair up with her, Leonard prefers Penny to, Penny prefers Howard prefers Leonard to Howard, and so she's not going to make that swap. Right. So an example of a stable marriage. All right, let's have a look at a model. So here we've got n men and n women. So for each woman, for each man, that woman ranks that man with this ranking value. Okay. So here's our black hole model. So everything that we saw before. Of course, here's an example of the data, right? So the layout, here's where all the cards are laid out. So these are the 17 piles, right? 37, card 37, then 36, then 18, etc., etc. So I can run my black hole model with this data. Oh, I'm running in gist, which I didn't really want to do. So let's stop that. Go back to G-code. Type error, undefined identifier layout. It's because I didn't run it with that one. Sorry. Yes, that's what I want to do. Okay, so you can see it's not that trivial an example with G-code. Eventually, I found a solution, right? So we've got the two different viewpoints being printed out, and you can see, sort of agree. Let's see this one that's easy. The card at position 1, 2, 3, 4, 5, 6, 7 is number 5. So if we go to position 5, we'll see that position of card 5 is number 7. Right, so we can see the inverse relationship there. So this doesn't change the system of constraints, but it's a new piece of information, right? And we can also make another observation. If we take S of I times I and add those up, that also has to be equal to N, right? So if we look at our example, 4 times 0, that adds 0 to this sum. 2 times 1 adds 2, right? Which is the same as these two ones here. 1 times 2 adds this 2, and 0 times 3, no 3s, 1, 4 is this 4. So you can see that the 4 times 0 is this, the 2 times 1 is these ones, which is exactly these ones, right? Because of this self-reflexive nature, this also is the same as adding up all the numbers, so it also gives me the same value. So we can add both of those to our model, and we can return a much smaller example. So, if you indulge me for one moment. Oh, actually, no, let's not indulge me. So redundant constraints can make a huge difference. So you can do this experiment yourself, because there's two models in the model files that I give you, separate from the tasks. There's this magic series and magic series with redundant constraints, and you can try out the versions with large numbers like n. You can see how quickly these redundant constraints reduce the solution space, the big difference between them. So I think I've reached the end of my time. Questions?